We said that neural network systems are going to represent objects or properties or relations in input and output layers by activation patterns, either by an individual unit or by a collection of units within that layer. Just as firing rates of groups of neurons can pick out positions in that representational space, like taste space or color space, activation of patterns across units in neural networks can pick out positions in a representational space, or each dimension corresponds to a unit or units in an input or an output layer for that system. In modeling, therefore, neural network theorists can choose to represent objects and properties in one of two ways. They can represent them locally, or they can represent them distributively. And the best way, I think, to think of the difference between whether some object or property is represented locally or distributively in a system is to ask if the vector representing that property is one of a set of orthogonal or perpendicular vectors. Essentially, they create axes within that space, so that the representation of that property is the representation of a single property along a single dimension. Or is the representation of that property or object actually a multi-dimensional vector, one that includes components from more than one cell or goes in more than one direction? In other words, is the representation of that property unidimensional within the space? Now, if our vector is orthogonal, if it's one of these axis vectors, then the property is represented locally. If the vector is not orthogonal, then the property is represented distributively. So looking at that taste space, we can look at it and now see that sweetness is represented locally. So just to be sweet, as opposed to be the sweetness value for some specific kind of substance. Just to be sweet is to go to be activated by the sweet cell, to move in one direction, the up direction. The taste of each individual thing within that taste space, whether it's table salt or citric acid or fructose or urea, that is represented distributively. It is a vector, that is a magnitude of activation across sweetness, saltiness, and sour, as urea here is. This far out in sour, this far out in salty, this far up in sweetness. Other examples using other sorts of systems. Here we have a system that represents gender and then the corresponding role one has in a family. And so in this system, gender is represented both binary and locally. So if you're female, this is activated. If you're male, this is activated. Same thing here for the role in the family. Brother is represented locally. Grandmother, aunt, father, mother, all represented locally. Needless to say, if you believe that gender is non-binary, then you'll have to come up with a distributive gender identity representation schema, which would presumably involve activation across a set of gender identity features. Here's a different way of representing light in terms of short, medium, and long wavelength activation patterns. And so we can see here, right, that the actual color of a particular light, that will be represented distributively. It's a combination of short, of medium, and of long wavelength light. That is the representation of that specific color. Wavelength, however, is represented locally in terms of one of those dimensions. Representations that are distributive are compositional representations. They're composed out of elements of these local dimensions, of these properties that represent a sort of subcategory, like shortness, medium, and longness of wavelength, that are components of an overall color of a particular light. So there's a compositionality to vector representation, but it's not the same sort of compositionality that we see with languages. With languages, you can sort of take words and put them together and take them apart like Legos, and you can recover elements of a sentence by decomposing the sentence into its parts. It's much harder to do that with these vector representations. They're composed of different things, but you may get the same vector space place in your representational space by different combinations of activation patterns. And so you can't decode a particular representation into its component elements as nearly as easily as you can decompose a sentence into its individual components. So next, we're going to want to look at processing and learning.